Good morning, good afternoon, and good evening. A warm welcome to all of you joining today from different parts of the world. Santiago, you seem to have impressed a lot of people across the globe. I am Sanjay Pichai, and it's my pleasure to host this webinar. Allow me to introduce our esteemed guest, Santiago Valdarrama. Originally from Cuba, Santiago immigrated to the United States during his formative years. With over 20 years of experience in building enterprise applications and machine learning systems, Santiago stands out as a true authority in this field. What sets him apart is his rare expertise in both classical and modern deep learning approaches to the computer vision. In recent years, Santiago served as the leader of computer vision group at Levitas, where he spearheaded the development of a wide range of computer vision applications for both enterprise and government agencies. His contributions have been instrumental in pushing the boundaries of this rapidly advancing technologies. He currently runs ML.School, a platform dedicated to educating and empowering individuals in the field of machine learning. You can also find his useful and insightful writings on his Twitter account at SVPino. It's spelled SVPINO. In addition, Santiago has been involved in fascinating projects utilizing Spot Dog and ChatGPT. It's all out there in the web, so I'm sure you'll all see it. Once again, I extend a warm welcome to Santiago and to each and every one of you. Let's start.
Thank you. That was long. Thank you very much.
I could write another page, but I must confess, this whole write-up was generated by ChatGPT.
Oh, there we go. Yeah. Very fitting. Very fitting for sure.
I thought, given the topic, that this is more appropriate to push our, the latest, greatest things evolving in the field of AI. So Santiago, glad to have you again. Would love to just fire up a few questions. And for the audience, feel free to send us your questions and we will interlace with the list of questions that we had prepared for it. Okay. So Santiago, today, computer vision and AI is becoming a hot topic in the industry. Wanted to set some questions here. Everybody talks about model, but we also want to look at what is the role of data in the field of computer vision and AI broadly, and how important is data quality relevant to training algorithms and shooting the model accuracy.
Yeah, it's funny because this morning I was writing a thread that I'm gonna post on Twitter next week, and it's precisely about this topic and the sort of like the angle that I'm taking on that thread is that, at least for me, every book I read and every course I go through, we usually hear about not having enough data. That's mostly what people tell you is the big problem out there, that you don't have enough data. And I understand why, right? So we're used to these academic data sets where you have just a few examples and all of these techniques to augment that data set, to balance the data set, to do all of that good stuff. What people miss is that in the real world, often that's not the problem. You have the complete opposite problem. You have too much data. And although it looks like too much data is a blessing, it might be better than not having enough data, but it's also a big problem. You cannot just take too much data and train a computer vision, especially when you're working with computer vision, because every sample is very big. So you will require a lot of memory, a lot of processing power. So if you have too many images, now the question becomes, how do I train a model that actually works when I cannot use all of the data that I have? So we're moving towards a world where capturing more data, it's very, very simple. Storage is not a problem, and the capturing devices are everywhere. And we need to build better solutions or put more focus on actually selecting good data out of those big data sets. That's something that a lot of companies are working on. Data is working on that. You guys, your solution is super cool. I've used it. And it allows you to take out of this sort of like an ocean of data, just take a snapshot that's actually representative of the overall data set. And it is actually curated in a way where you can actually train a model that's very good without having to spend the money or the time training with all of it. So it's very, very important, focused on better data. I have actually, let me see if I have it over here. I don't know what it is, but I usually have this big sign that says better data is better than better models. It's using the word better 3 times. It's kind of funny, but anyway, I think there's a lot of focus there right now. That's pretty cool.
Well, thank you. Yeah, we have seen that time and again in some of the select fields in the modern decade. One of the front-running industry is the autonomous vehicles. Mm-hmm. And as you can imagine, each of these cars are fitted with tons and tons of visual sensors. They produce way too much data than one can actually absorb. And some of the points that you resonated or you mentioned resonate with that.
This is what's funny. If you think about that example, right? When you look at the data set after, you drive many, many miles, and when you look at the data set after doing all of that, 99% of the data set is going to be about data that is actually not that interesting. It's going to be pictures of driving on a highway, because many people drive a lot of miles on highways, or honestly, situations of day-to-day life that are not that complicated to navigate for the car. However, you're going to get just small percentage of pictures, and those are the ones that you actually want to use to train your model. Those are the ones with the road block or somebody stopping traffic, or I think Karpathy showed on the AI Day a couple years ago how they generated picture of people running on a highway. Those are samples that are really hard to find. And if you just rely on taking a random sample out of your data set, you will never get. So you need more sophistication in order to select your data.
And with your experience spanning across diverse range of projects, and I just called out autonomous vehicles as one of the front runners. What other areas have you worked on?
So I have a good example. It's I cannot say who, so I cannot name the client, but it's a big company that everyone knows. And let's imagine it's a fair, right? So it's a big area where they let people in, but you have to pay to get into that area. So this client wanted to solve a very specific problem. They wanted to understand whether there were many people coming into the area without paying. Okay, so they actually wanted to understand if they needed to spend more money, maybe hiring more security, maybe increasing, I don't know, whatever it was to prevent people from coming in without paying. Excuse me. So they installed cameras pointing to the area where people come in, and they started recording. And the whole idea was, let's build a computer vision system that will track people as they come in and automatically determines whether people pay to come in or not. So long story short, at the end of the project, we were able to determine that it is indeed a big problem for them. We're talking about millions of dollars a year lost because people just, and it's super funny seeing people just coming through not paying. Like they literally never stop. They just go, and there is a lot of people always. That's why they can do that. Plus the people who work for this company have orders not to stop anyone. So even if they realize that you're coming in, they might talk to you very softly, but they will never get into a confrontation. So it was funny to see all of these videos. That's one example of a computer vision project that we've worked on. There are many, many other examples in the industry. I've also worked a lot with Spot, and specifically with Spot, it's about taking pictures in industrial settings, for example, of analog gauges. This is something funny. I've never thought that it was possible, but factories right now here in the States, there are thousands of gauges inside these factories, thousands of analog gauges, not digital gauges. You would have thought that in 2023, digital gauges was more common. They're not. It's analog gauges. So if you really want to inspect all of this equipment, you will have to send somebody with a pad, and paper, writing down what the reading is for each one of these gauges, which is obviously impossible to do. Companies don't do it. So by automating the process of reading those gauges, not only we can actually get a reading really, really quick, but we can also do it many, many times, a day, a week, whatever frequency we want, and do preventive maintenance. Like basically we can detect when equipment is about to break, because maybe the pressure has been increasing for a couple of weeks already, right? It's still not run, but the pressure has been increasing steadily for a couple of weeks, and we can go and check that equipment and prevent equipment from breaking. So those are some examples where computer vision really, really helps.
Thanks, thank you. And really surprised to see analog gauges still in effect.
It is. I mean, honestly, I thought, why don't they, that the first time I heard about this, right? I'm like, well, let me just give you an Amazon link with a $4 digital gauge. Just get rid of your analog gauge and just put the digital gauge. And it doesn't work like that. Digital gauges require power. In some of these locations, you cannot run power. Imagine a nuclear plant telling the people that work there, the facility, well, you have to run power lines just to power your digital. It doesn't work like that. Yeah. So yeah, analog gauges are very, very common. Yeah.
Great, thank you. So referring back to
somebody asked really quick, just so we don't forget the thread there. How did they determine who was a paid customer in the first example and who was not? Well, when you're a paid customer, you have to stop and give your ticket to the people attending there. So it was all about the pattern that people took in order to come into the area. So some people went just straight in. Some people had to actually make a stop and get closer to the attendance there. So that's how you determine if somebody paid or didn't pay.
So I'm assuming you use both data or metadata from that system as well as your own.
We did not. So there was no metadata on the system. This is just pure vision. So just by doing people tracking, and we were able to determine based on their trajectory of the people, we were able to do an estimate of who paid and who didn't. All of that data that we selected then later went into humans, that humans were the ones watching the video and deciding, oh yeah, this is a positive case or it wasn't. But imagine hours and hours and hours of footage. It would be impossible for a human to just review all of that footage. So what we did was just reducing the haystack, right? This is like finding a needle in a haystack. Our job was to reduce the haystack to a size that was manageable by humans. So we detect everything that we thought was a positive case, somebody breaking in, and we send those clips to a human, and the human just review them and say, yes, no, yes, no, yes, no. That was the whole idea.
Okay. Yeah, so I think related to that, there was another question to how did they determine who was a paid customer and who was not?
Yeah, remember, the whole goal here is not to stop these people. The whole goal is not to tell them anything, or the whole goal is to understand whether further investment is required, right? It's like, is this a big problem, right? You know how much people pay for tickets. If you can compute how many people break in or don't pay, you will have an idea of how much money you're losing. So again, if you see somebody coming with their ticket and they stop and deliver that ticket, then you can assume they are a paid customer. If you see them going through the gates without stopping, without showing the ticket, now you know they probably didn't pay. That's the whole idea.
Um, one more question. Actually, questions are lining up. I should probably put aside my questions that I had prepared. The other one is a person called out. He would be interested to hear some applications of computer vision in the construction industry. Could you name
So
something?
yeah, no, I've seen some examples. I personally have not done anything specific there, but some of the examples there are for PPP. That's personal protection PPE. Sorry, PPE detection. So personal protection equipment. That's just to ensure that everyone in the construction site is wearing a hard hat, glasses, and a reflective vest. Those are requirements, but you know how people are. So you can have cameras flagging any time that somebody's not wearing PPE and sending an alert to maybe the site manager, for the site manager to go and say, hey, you have to put your glasses on. That's one thing. The second use case that I've seen a lot in the construction side is detection of equipment that's out of place. So for example, a ladder is not supposed to be in a specific location, but people, construction workers just forgot the ladder there. They forgot a forklift in the middle of a road. They put a bunch of boxes next to, a place that's dangerous. So detecting all of those out of place equipment, pieces of equipment, or whatever it is, that's another big use case in the construction industry.
And another individual had asked, I work in the medical field where obtaining data is probably more specific. There are issues with patient protection issues, with proper labeling, getting data from various sources, etc. Can you comment on ways to overcome this, on modern approaches as to how to make the best use of limited data sets?
Yeah. So I mean, how to make use of limited data sets, is that's the end of it?
Yes.
Okay. So for limited data set, I think, I don't know if there are any modern approaches, and you tell me if you know of anything. Usually the stuff that I know to work with small data sets has been around forever, which is how do you do augmentation of the data, for example? How do you do sampling or better sampling of the data, like oversampling minority classes, undersampling majority classes in order to find a better balance of your data set? But it's mostly about augmentation, and it's mostly about generation of data that's fake or synthetic data. So those are usually where the techniques go through. On the other side, you get the opposite problem, which is the one that we talked about before, where a lot of companies are using embeddings to understand images a little bit better, to cluster them, and to actually find good data or good samples inside the sort of like the world of your data there. Hopefully that helps a little bit.
Yes, indeed. And I'm glad you called out the synthetic data, because there's either too much data, of which the data of interest is often a small representation. Now there's a challenge of how to go about finding that. Now, after you find, you realize you have few. Now, how do you go about augmenting that? And that nicely tees up with your generative or synthetic data.
Yeah.
But there's another individual who's asking some career points. Where does one start the journey as a computer vision person, as a beginner?
Okay, so how do you start? So I'm gonna tell you how I started, and you're gonna realize, hopefully, that it's really not that hard to start. Okay, so I started at school while I was taking my master's. I had to go through computer vision classes. There is a book there that I'm going to do you a favor, and I'm not gonna show it to you. That it's a very thick book, and it's about what we call classical computer vision. There's so many formulas inside that your mind would blow outside of your head. Just a lot of math. And that was the computer vision that I took in college, right? I remember one of the projects that we had to solve was a car with the trunk open. Okay, so there is a picture of a car with the trunk open and a person holding the trunk. And we had to transform that image in a way that showed, sorry, we had two pictures, the car open, the trunk closed. And we had to generate the intermediate pictures, okay? So starting with two pictures, the beginning and the end of the sequence, we had to automatically generate the in-between. And the best solutions were horrible. I mean, if you see
It's a little bit of a freeze.
obviously techniques and whatnot, those are the ones that you usually use with a library like OpenCV, all of those transformations and stuff. And then deep learning came in and changed the field. Deep learning did not replace everything that you do in classical computer vision, but it did take over a bunch of different use cases that were impossible before or just too hard. Like I remember how we did face detection before, and it was the age transform. I don't remember the name of the thing. And right now you can do that in deep learning really, really easily. So if I were to start right now, I would try to start by taking a course on deep learning. And then when you take a course on deep learning, they're going to show you sort of like two paths. And one is going to be for natural language processing, and the other is going to be for computer vision. And you will go down the computer vision path. You're going to start learning stuff. And that will be one component of what you need. And the second component will be the classical computer vision stuff, which is going to be less than the one I had to go through. So it's going to be much less because now deep learning is taking a big part. But you're going to start learning those, the different courses online and whatnot. That would be my recommendation. There is, I think, Stanford. I'm not sure if it's Stanford or Amazon, the ones who published a full computer vision class online. You can go, like on YouTube, you can go through that. Perfectly valid way to start, and it's going to be really cool. Yeah, that's what I would do.
Thanks, Santiago. And maybe after this webinar offline, I'll collect some of the pointers that you can collate. We'll share it with the rest of the audience. And I'm sure you post regularly so people can really take advantage of the contents that you're producing. A couple of more questions. How are you seeing and utilizing synthetic data as part of these projects? What tools do you recommend using here?
So to generate synthetic data, so that's yeah. So in my experience, I don't have a specific tool, but my experience is highly dependent on the use case. Like for example, Tesla uses a video game to generate synthetic data. They mentioned that, or at least they used to use a video game with street photography to generate synthetic data. So synthetic data, it's not, although it sounds like a great solution, you gotta be careful with it. Because the quality, if you're not careful with it, you're gonna be training a model on data that is not real. And if you do that, as soon as you see real data, you're not gonna get great results. So generating pictures that are synthetic, it's very complicated. Let me give you a few examples that actually I've seen work. So one of them is for gauges, okay? For analog gauges, it's not that hard to generate synthetic data because you can actually start with the dial and you can remove the needle, and now you can position that needle wherever you want. So you can generate a lot of synthetic data that looks exactly like the real data, by just moving the needle around using just formulas. So that is a cool way of generating synthetic data. For that use case, we didn't need to use a tool. We did that ourselves. For thermal imaging, it's also very easy because it's just a blurb of color. So you can manipulate the blurb, like by the blurb. I don't know if you've seen a thermal image, but you cannot see what's happening. It's actually different colors will tell you the range of temperatures. So if you get the hot area, you can actually sort of like move it around a little bit, and you can put it whatever you want to do different things. So that also is very easy. Now, how do I generate like a real looking scene? That would be way harder. Like what Tesla does with the video games, that's way harder than what I've done. And you will need for that like a rendering engine. You will need something else for that. Just be, understand that you have to be careful with generating synthetic data. You have to have the proper sort of like balance between real and synthetic data. Synthetic data is great for augmenting, not necessarily for taking over the entire data set. So hopefully that helps.
Thank you. Yeah. And some names to call out, the companies in the auto field, a company called Applied Intuition, which generates high quality synthetic data. Another company that we are very familiar and partner with is a company called DataSpan out of Israel. They do some interesting work as well. And there are many other things that we can probably share that information with the broader group. More questions lining up. So in the interest of time, I'll start going. One of them called out, they're today more of an NLP engineer, and they wanted to see how extensible are those concepts in the field of computer vision.
From NLP?
Yes.
There are a lot of stuff that are, when you're working with deep learning models, a lot of stuff, it's perfect crossover. Like you're still working with big neural networks. And if you understand how these big neural networks work, you can do a lot of stuff. Like, for example, you can use recurrent neural networks on computer vision as well as on NLP. They actually were first created for NLP and later applied to computer vision. The project that I just told you about the people coming in, we did use a recurrent neural network, which again was first created for NLP. And the idea of the recurrent neural network there that we used was to add the time component. So if you think about a video, what you did 1 second ago matters as much as what you're gonna do in 1 second. So there is a time component there where we have to see your whole trajectory. And we used the same architecture network that you would have used for a natural language problem. There are differences, but there are also a lot of commonality. Yeah.
Okay. So other person, I'm paraphrasing that, the fact is that you end up training models, but often these models have to be deployed at the edge of the network, where the resources, compute and connectivity resources, all of them are limited. How do you make that into your design? As you know where this model is going to be deployed, you're training these models probably in a cloud or somewhere. What are the steps that you recommend while they build?
So some of the platforms have ways to deploy on the edge. Like for example, Amazon has a whole thing, it's called Greenfield, and you can do edge deployments with the platform. And basically they take care of a bunch of possible steps that you might want to take, like quantizing the model, making sure the model is properly optimized to run on low power hardware, and you can do stuff like that. If not, the whole idea here is it doesn't change a lot. You have to think about what are the actual limitations that you have when you deploy on the edge. For example, we've done a lot of deployment on the edge because of Spot, which is a robot. So it's just moving around. And the main limitation is not necessarily hardware, because we do have the hardware there. We have GPUs, we have just a full-fledged CPU. We don't have that limitation. It's not like a camera that needs to run like a small little model or a mobile device. So our challenges are different. Our challenges are, how do we get models from the development environment? How do we push them to the endpoint, right? Which is the Spot unit. So that's, there's a quiz here in front of me, sorry. It just came in front of my face. So usually the challenges that we had to go through there are about process, not necessarily about tools. So the tools were the same as we were just deploying models in the cloud. They were more about processes. How do we create the processes to update those models, to version those models, etc. What we did, just in quick summary, is we abstracted away all of that complexity. We imagined that those models are going to a normal cloud environment, and there was a final step that we had to do manually anyway. And that final step, by manually, what I mean is when you put together the software for a robot, the version, we create a package, and that the latest package is the version that's installed there. So it acts more like you would like a Windows installation, for example, that you have this package that version 3.3, and you can decide which package to install on your computer. There is no automatic updating, nothing like that works in what we did. But yeah.
Great, thank you. So another question is, since your experience spans across both the classical computer vision and then you also embrace the deep learning approaches, is there one specific types of certain use cases that yields well for classical CV, and then other use cases might yield well for deep learning? Are there patterns? Can you call a few?
Yeah, for sure. So anything that's detection is usually very good. Deep learning is very good at detecting things. By detection, I mean detecting people, detecting bicycles on a picture. If you're doing self-driving, detecting cars on the road. But there are things like, for example, the gauge detection that we were doing, not the gauge detections, like the analog gauge. There are two steps. We do gauge detection first, where we use deep learning to do that. But the reading of the gauge, we tried. I promise it was too hard to do reading by just showing many examples to a network. So instead, what we do is we detect where the needle is, we detect read the numbers, and we do math in order to compute what the actual reading is. And I'm sort of like hand waving my hands here, or I'm doing some hand waving here. It's a lot of code, but it's mostly classical computer vision code. It's not deep learning, because we cannot get a reliable reader for gauges. So there are problems like that you're going to be better off just using classical machine learning. Not only gauges, we did, there is something that's called sight glasses. And, if you've been to a factory, you've seen those. And that's like a hole with, there is glass and there is a liquid inside, okay? And you have to, so you look at the level of the liquid, and that is your measurement, okay? So you have to see what is the level of the liquid. And what is empty, when it's full is full, and it means different things, right? And how do you do that? Well, we detect the sight glasses. So we detect the hole using deep learning. That's very easy to do. And then you can do the reading, the level, to determine how full it is or how empty it is, just using classical machine learning by looking at lines and computing what is the best fitting line and doing stuff like that. So usually a combination, that's what you're going to have to do at the end of the day.
Good. Okay. Thank you. More questions from the audience. So, are there, what kind of sensory video hardware is typically needed to just get started on the computer vision projects?
I would say very little now with the cloud platforms that we have. Like, you can have an account on Google Colab and go through classes and do a lot of stuff. Here's the good news, and this is the way what I usually tell people. The minute you need to do something serious and you need serious hardware, it's because you're working for a company that's going to be paying for that hardware. So don't worry about that hardware, okay? To go through a course, to go through tutorials, to learn what you have to do, you almost never need anything fancy. And you can get away either with your computer or just with a Google Colab subscription, which is going to cost you $50 a month. Again, it's not cheap, it's not necessarily free, but you don't need to pay for a full-fledged AWS SageMaker account and spend a bunch of money on GPU hardware. No, by the time you need that, you're working for a company that's actually trying to solve a serious problem. They will be paying for the hardware. So I wouldn't worry about that.
Okay. And one question, this must be early on in the cycle, probably a reference to the use case you were talking about, cameras detecting people to entry, which says, did the system improve after human validation, or the system only did the detection and tracking, and humans in the loop were deciding the rest?
Okay, so yeah, great question. This is probably related to the problem of people coming in. So our goal here was just to leave it after So we did, again, we reduced the haystack. We sent the clips to people for them to review, and that was it. That was our job to that point. Now, you make a great point. In an actual system that's actively trying to detect people coming in to do something else, you could have a human in the loop component and then allow the system to improve by using the responses of people. Very easily you can, not very easily, I'm sorry, but you can definitely incorporate that feedback into your next training session in order to improve the system. We did not get there. That wasn't our goal or our job. Our job was to put something together to just determine if there was a big problem there.
Thank you. And this might be related to this, but even broadly speaking, there's been sometimes companies enter into hot water because of unintended consequences of their ML as well as computer vision applications. Very specifically, I'm talking about biases, right? And inadvertent consequences to that. So, could you talk about a little bit of natural biases in the data sets, and when you're connecting that to the real world data, how do you ensure when you go into production that it doesn't end up doing something really stupid, and next thing you know is your company's name is all over the Twitter feeds?
Yeah. So, well, first of all, there is a reason why I'm not disclosing the name of this company, okay? And it's precisely because while we were talking about that project, we did not want the name of the company all over the news saying, oh, they're employing computer vision to track you. Again, they were not making any decisions with the system that we built. It was just to understand if there was a problem. But in order to do something different with that information and with those models, you will definitely need to be more careful. So the reality is that deep learning models and these big models that we're using right now are in part they work like black boxes, and it's really hard for us to determine what is sort of like the decision-making process of one of these models to make a decision. We don't know exactly what happened. So a lot of the emphasis, because we cannot put it on the model, a lot of the emphasis goes into the data. And how can we better source data and select data that's going to minimize biases? So let me give you one example here. I made up this example, okay? This is completely made up, but you're probably gonna understand how it works. So imagine a bank, and probably if you're in the United States, you have your bank supports taking a picture of a check and depositing that check, okay? I bank with Bank of America, they support that in their app. So I get my phone, put a check and take a picture of the check and reverse the check and take another picture, and that check is gonna be deposited. So now this team created this for the first time, integrated it with their bank, and after some time they went and looked for some statistics. And what they found is that the percentage of wealthy people depositing checks was way higher than the percentage of poor people. It wasn't just about the number of the checks, okay? So it's the rate at which they actually used the application. So they wonder what's going on here. Is it education? Like, why poor people are not depositing their checks using the system at the same rate, right? So they dig a little bit deeper, and they found that they were actually attempting to deposit the checks. Like when you looked at the number of people, of wealthy people trying to deposit checks, and compare that to the number of poor people trying to deposit the checks, the numbers were different. But the poor people, the images coming from poor people less wealthy, were bouncing, were not going through. And it was all about the actual quality of the images. So this team built a system using high quality images of checks, images that were taken with the latest generation of phones. And when they released that, they actually, people that don't have that type of phone, they could not use the feature, right? So they had to actually walk over the bank and deposit the checks. This is one case where the sourcing of the images did not take into account this type of problem. And that's how you, with something as simple as this, right? That's how you bias your model to accept one type of picture and not the other.
Thank you. The other question is, probably this is related to some of the sensitive projects that you work on, where you talk about government agencies and other things, even some of the large enterprises. Data residency is a big issue, particularly with computer vision data. And here you are expected to go solve their problem, and they're not going to give full access to their data, whether it be in their cloud or their data center. And also, the second part to that is once you deploy the model, you don't have full visibility how your customer ends up using it. So, what are the issues, the practical issues you have stumbled upon, and how did you circumvent that? Any advice?
Yeah, it's I mean, when you go and work with some of these companies, to start with, some of these companies don't even use the cloud. It's just incredible that you talk to them and they don't want to use the cloud. It's not lack of expertise. It's not lack of anything. It's like they're very protective with their data. They understand that data is gold, and they are very, very afraid that if they upload the data, let's say to AWS is going to use that data to later put them out of business, right? So these companies, number one, are very protective of their data. So usually when you go and work with them, you have to work, I've worked with proxy data, which is super fun. So proxy data is basically, they don't give you the data. They give you proxy data that's modified for you to use it. So this big project that we've been talking about, is funny because there is a lot of stuff that happened on this project of people coming in. The data that the images that we used to train our model were all faceless, because they took the real images coming out of the cameras and pre-processed all of those images to remove the face of people, because we did not, as an external vendor, we did not or shouldn't have had access to the face of people. The extra challenge here is that you're not even working with the real data that your model is going to be seeing. You're working with proxy data that's very close, but not necessarily the same, right? So again, how do you do with that? You have to adapt. You have to use all sort of mechanism where you train something here and then train something there and compare the results and try to make it better without full visibility. Like you said, oftentimes when you deploy your model, you don't even get access to actual production data. So you have to sort of like create a mechanism for computing what the results are of your model, what the performance is, but you don't necessarily get access to the full data. By the way, which is something very interesting, companies are working on right now to create mechanisms. So imagine how much personal data hospitals know today. And many people believe that we will, if engineers were able to use that data and pull it together from hospitals, we will be able to solve maybe illness that are not, we will be able to make a lot of progress in medicine. So like the challenge is, how can you, nobody wants their personal health information shared. So companies are working on solutions where you can actually train your model on remote data without you ever seeing that data. And it's pretty cool. I've read a little bit about some of the companies that are working on this. It's pretty awesome, because imagine you're building a model using data that you have never seen and you will never have access to. And all happens remotely with data downloaded to your computer, but really quick, and then it goes away. And it's such a huge thingy. I think it's very interesting for sure.
And I know we are already past the time, but if there are so many more interesting questions coming up, Santiago, would you 2 minutes more? Could you stay longer? All right, thank you. So we'll cover these questions. One is, where do large language models fit in the machine learning hierarchy? Is it machine learning or is it deep learning, NLP? What is it?
Yeah, it's deep learning for sure. These are very big neural networks that are happening. So you can classify them as deep learning. Whether or not we want to create like a separate space or like a specific category for them and call them large language model, that's to be seen. We're figuring this out as we go. Okay, so it's not like we're literally inventing this type of stuff right now. So it's not like we have a template and large language models should go into, no, we're just inventing this. Again, they are part of natural language processing. They are part of deep learning. Whether or not we create a special category for them is to be seen. But yeah, that's where they belong.
Okay, so two more questions, one of which is something I had wanted to ask. I'll reserve that as the last one. I prepared like 25 questions. I asked only one so far from my own list. But let's start something individual asked, which is specific to what you discussed. Your bank check use case is an example of selection bias prevalent across computer vision problems. For example, in radiology, an initially published paper shows incredible accuracy, but once radiologist starts working with a model, it does stop to work, right? So they're talking about the disconnects between probably more of a theoretical space to, and the papers published, but when it comes to real world, it's it's broken.
Yeah, there is a sample now that you mentioned radiology, and I do not know where I heard this example, but it's a real one where they built this computer vision system that took X-ray images to detect specific sickness, if the patient was ill or not. And the model was really good. And what ended up happening was that the model was actually reading, there was handwriting on top of some of the images. Like the doctor that took those X-rays wrote with a pen something on the images. That was the information that the computer vision system was using at the end of the day. As soon as they trained their model, it's doing great. We solved the world. And when they went out and started testing with other images, they realized the model was really bad. And it was just because the model was picking up the handwriting and was using that as a signal to determine whether the patient was sick or not. And again, nothing to do with what we're talking about, but I think it was an interesting case of not having a good data set in the first place in order to train your model. So.
Yeah. One last question, I promise, which is, is closer to me as well. Big company or small company, there's always somebody in the leadership who's making a, or taking ownership of the AI program as a whole. They have to start estimating the man months, the dollars, budgets, and everything else. They all come up with certain things, gets going with the project. What are the things that they're completely blindsided, and how often these projects get delayed, overblown in budgets, things of that nature?
Yeah, I mean, labeling is one of the things that it's nobody thinks about that. People think that just creating labels is very simple because, of course, it's cat, dog, cat, dog. As soon as you start working with a problem that requires subject matter expertise, now it's not that simple. But even with cats and dogs, when you look at some of the pictures that you capture in real life, some of the answers are not obvious. You get a lot of, you get people telling, some people are going to say that's a cat, some people are going to say that's a dog. And you have to actually get into consensus validation. How do you determine whether this is cat or a dog? So labeling, there is a lot of, usually people forget about how difficult it is. Even the capturing, the maintenance of that data, how do you store that data? How do you make it secure? How do you capture it frequently enough for us to train models? So those little questions that at the start, you usually sort of like put them all together into, we have a data set. Well, actually, when you dig deeper, you realize that there is a lot of work to be done to get to a point where you have a good data set to train a model. There are a lot of questions. Even what data do we need to capture? That's a big question that people usually don't think about it until you start realizing and talk to business people and start realizing, oh, actually, what we need to capture is not what we thought we needed to capture. We need to capture it this way. So anyway, those are some of the things that are usually blindside projects. Yeah.
Well, thank you. And actually, there's tons of other questions. I don't think we can cover this in the session. We want to thank all of you for joining, and Santiago for specifically staying longer and sharing your views. Uh, I'm capturing the reminder of the questions. Perhaps I think we might have to do a webinar 2.0 or a sequel to this one, probably double clicking on some of the technical aspects. Thank you
Okay.
so much. We all appreciate you staying longer, and have a good day.